𝐂𝐨𝐧𝐭𝐚𝐜𝐭 Bismillahir-Rahmanir-Rahim. I am Hamad Abbas, your host. Welcome from the platform of Quanta Publishers. I am professor at Department of Physics, Emerson University, Multan. Last time we have studies about the basic introduction about vectors, scalars, addition of vectors, subtraction of vectors. Today our topic is about product of vectors. Dear students, there are two ways to multiply the vectors. First of all, we will talk about product of two vectors. And in the next section, we will discuss about the product of three or more vectors. The product of vectors is categorized into two parts. First one is called scalar product. Scalar product is defined as if the product of two vectors resultant is a scalar quantity. That is, we multiply two vectors and then we get a scalar quantity. Then that type of product is called scalar product. Scalar product have many applications in the physics. Before going to the examples, we will try to mathematically interpret the scalar product. Let we have two vectors, A and B. Like this is vector A and this is vector B. We want to multiply vector A as B. Here we can write the scalar product as a dot product also. Because of this type of notation dot, we also call scalar product as a dot product. So we want to multiply A as B and we will call this as A dot B. We want to find the magnitude of A dot B. Then its simple meaning is that we want to join vector B with a vector A from here to there, here to there. It means we need to draw a perpendicular or a projection from B to A such that we may able to combine B and A. Now, vector B is resolved into two parts as a vertical component and horizontal components. The vertical component is called B sin theta and horizontal component is called B cos theta. Now, this is the total product of two vectors, A and B. That's why we call A and a projection of B on A. This is equal to AB cos theta. Similarly, we can also rewrite as from B to A. If we want to multiply vector B with a vector A, then again same process is repeated. Now we will draw the projection of A on B like this one. Sorry, here. Now we will draw the projection of A on B from here to there. Then we will read as vector magnitude of vector B and projection of A on B. That is also equal to BA cos of theta. It means that scalar product have same result like A dot B or B dot A. Either from A dot B or B dot A, we will get the same resultant AB cos theta. These are some examples commonly used in the physics. For example, work. We know that work is a scalar quantity. And this is a product of two vectors, force and displacement. That's why we call this product as a scalar or dot product. Similarly, power. Power is a product of two vector quantities, force and velocity. But power is a scalar. It means that the product of these two vector gives a scalar. That's why we call this scalar product. Similarly, electric flux or magnetic flux, E dot delta A or B dot delta, that is equal to electric flux. Or if there was magnetic flux, then we can write here B dot del A. Del A is a surface area or vector area. Now we will proceed about the important features or characteristics of scalar product. From the above explained mathematical interpretation, we find here A dot B is equal to B dot A. That is the resultant of A dot B and B dot A is same. That's why we can say that scalar product is a commutative. Commutative means either we multiply A dot B or B dot A. There will be no change in the resultant. That's why we call scalar product is a commutative. Next one is the scalar product of two vectors is maximum when they are parallel. For example, parallel mean we can draw a rough sketch here. Let's suppose this is the vector A and this is the vector B. These are called parallel vectors. These two parallel vectors show that theta is 0 and cos 0 is equal to 1. Then we will got the result AB cos 0 and that is equal to AB. Their unit vector can also be described in case of parallel. Because unit vector have magnitude 1, we will put here 1, here also 1, and 1 multiplied by 1, that is equal to 1. Like J dot J or K dot K, they are all equal to 1. Now the scalar product have the minimum value when they are perpendicular. Perpendicular means theta is 90. Then cos 90 is equal to 0. So we can write here A dot B is equal to AB into 0, that is equal to 0. Similarly, their unit vector can also be written as I dot J, that is equal to I magnitude, J magnitude, and cos of 90. I magnitude is 1, J magnitude is 1, and cos 90 is 0. That's why I dot J is equal to 0. Similarly, J dot K is equal to 0 and K dot I is equal to 0. This is again same procedure. Self product mean two vectors, equal vectors in the same direction or same magnitude. Then theta is 0, cos 0 is equal to 1, and we will get A dot A is equal to A square. Similarly, any vector can be replaced from vector A. For example, if there is a vector velocity, here is a velocity that is equal to V square. And in the last distributive property of scalar product is very simple. If A dot B plus C is equal to A dot B plus A dot C. Here C is, I think, missing here. We can write here A dot C like this one. Now, similarly, A dot A plus B dot C, that is equal to A dot C plus B dot C. In case of rectangular components. Rectangular components mean a vector with all its components. For example, if there are two dimensions, then we can write here A is equal to AXI, AYJ, and B is equal to BXI, BYJ. For three dimensions, there are three vectors, components, X, Y, I, J, and ZK. That is equal to A dot AX dot BX, that is equal to 1, because I dot I is equal to 1. Then we will got AX, BX. Similarly, AY, BY, AZ, BZ. This is a simple case. The other rest of the parameters like ax, by, ax, by will multiply with their unit vector I dot j. They will equal to 0. That's why we will not write here. So then simply a dot b is equal to ax, bx, ay, by, az, bz.